Hello, my name is Björn Hermann, and in this short presentation, I will provide you with the basics on how to create nice-looking scientific figures. Since most of our empirical research involves having some data, we eventually need to represent those data in figures on posters and talks or in manuscripts. But why would we bother with aesthetics in our scientific figures? You may say, as long as my figure shows the relevant information, I'm good, I don't need to worry about that. But I'm suggesting that there is a little bit more to it and that your research will benefit from thinking about aesthetics aspects as well. Here are a few points on why having nice looking figures may be beneficial to you. On the one hand, readers often scan papers quickly before they actually read it. So they either scan some text or they check out the figures. And nice looking figures may motivate the person to dig a little bit deeper and read your paper in more detail. There are also some developments in publishing. For example, you may provide a graphical abstract with your figure, or you may consider putting a trimmed version of a figure into the cover letter to the editor when you submit your manuscript. Moreover, more and more journals encourage that you not just represent data as bar graphs, but also show individual data points or other ways of representing your data. Nicer looking figures may also help you with the recognition of your work. So for example, nicer figures may help the reader to remember your paper, it may help the reader to understand the results better, and it may also make the reader trust you more on the results. So anything you can do to make the reader trust your data and like what they see may help them remember your work better and cite it in their own work later. But having nice figures may also have other benefits for you. It may improve your talks and make them potentially more engaging. But by thinking about how to best display your data, you may also understand your data better because it takes a little bit of time to think about how to represent data best. One thing you will notice when browsing through high-impact journals is that they often have nice-looking figures in multiple panels, and they often provide lots of information with very little space. So let me show you a few examples that are done fairly well. In this figure from a paper published in Nature Neuroscience, you can see it provides details about the experimental procedures. It has some information about time course data and also shows some average responses as a function of visual contrast. This is another figure from a paper published in Nature Neuroscience. Again, there's some information about the experimental procedures up here. It shows neural data for different conditions, for different animals, and as well as behavioral data down here, and represents a lot of data in a reasonably sized figure. Figures showing fMRI data often involve one or more images of the brain. For example, here on the left. And in this particular example, you can also see surface maps of auditory cortex that are provided for each participant. And these lines here represent the orientation of Heschel's gyrus in auditory cortex. These three example figures give you a little bit of a flavor of what I mean by aesthetically pleasing and nice looking figures. And figures are overall a little bit like good photographs. You would want people to enjoy looking at them, even if they do not fully know what it is that makes the figures really so appealing. In order to start thinking about good figures, I will show you a few examples that still have room for improvement. This is a very simple figure showing data related to some treatment. And yet there are several things that could potentially be improved. For example, the symbols are really small and they also look very similar, so one cannot really distinguish well between the different conditions. Another point is that the x-axis is fairly wide, so one could consider squishing it a little bit. That would emphasize the effects in the data and also save some space. The font sizes on the x-axis and the font size on the y-axis differ. So the font size on the x-axis is larger than on the y-axis. This is something small that we may consider and just avoid. But there are two other points about the y-axis that could be potentially improved. On the one hand, one could remove the dot and the zero because it doesn't really provide any information. And on the other hand, the numbers take up a lot of space here. So one could divide them by 1000 and just present 1.2, 0.8, 0.4 and change the unit of the y-axis label and thereby save a little bit of space. There's also something to say about the figure legend, providing the labels for the different conditions. But the condition labels differ in the figure legend compared to the figure caption. And ideally, there would be some consistency. A last point, and that only sometimes works, is that the conditions here, this is no treatment, this is treatment 1 and this is treatment 2. So one could consider changing the order of the figure legend so that it represents the order in which the data are plotted here. But that only sometimes works well. So these examples show you that even a simple figure like this could be potentially improved to be more effective, more space efficient, and potentially also more appealing. Other things you may want to consider is avoiding plotting unnecessary dimensions. So plotting 3D, for example, sometimes appears to look really nice, but it can really limit information you can gather from the figure, for example, from back here. So in this case, it's better to represent the data on a 2D plot where you can really get all the information. This also applies to a common output from Excel where bar plots are plotted in 3D, which makes it a bit more challenging to estimate the differences between the different conditions. So this could just be presented in 2D. Thinking about space and white space is also very important when creating figures. In this example here on the left, the figure is overall too big, so it takes up the whole page. And that means that the figure caption is far away from the figure because it's on the next page and it requires scrolling when the reader reads it in a PDF, for example. So it may be better to limit the size of your figure such that the figure caption can fit on the same page when in print. In the example on the right, a lot of white space is left unused. For example, here on the left and on the right, nothing is really displayed. So it may look better if one were to use this white space, and it may also help to reduce the length of the paper. For example, if this plot would be here on the left, and for journals that require you to pay page charges, a shorter paper may also be financially beneficial. Always make sure that your figure provides all the information so that the reader can understand your data. In this example, on the right, you can see MEG topographies, but the color bar is missing, so we don't really know the magnitude of the neural response. But there's also some other aspects about this figure that one could potentially improve. For example, the font type is different between the title and the label relative to the numbers provided on the x-axis, and we could just choose using the same font type throughout. Another small interesting example is this one here, the label on the y-axis. It is plotted in an art-typical orientation. Usually, you would read the y-axis label from the right, so it's plotted in the opposite way on what would be typical. And this just emphasizes an interesting aspect about making figures, and that is that usability aspects really matter. So you do not want to break with basic habits of how people look and view figures, or if you do so, you only want to introduce very intuitive new features so that people can still rely on their usual viewing and looking habits. This example is not so much about aesthetics. The figure here on the left shows data plotted on the black background. But what that means is that if a person prints your paper, more ink or toner powder will be used. And for light black, an ink printer may even produce a bit of a reddish looking background here because the printer may mix black from different colors. You may also end up with a pretty wet page if the page is printed with ink. So you could just avoid this by using a white background, such as in the example on the right. I would like to now briefly talk about the vector graphics because the final figure for a paper may be created with a vector graphics program. What is a vector graphic and what is the difference compared to a pixel graphic? We may use the circle as an example. Vector graphics are based then on a few control points, so it's not needed to, or doesn't need to save all the information of the circle, but the circle can be described by 3 points only. And so the vector graphic saves these 3 points. And the advantage of this is that the graphic can be scaled up and down, so one can zoom in and out without any quality loss because it's always described just by these 3 coordinates. And vector graphics are really powerful for lines, surfaces, dots, and areas. Pixel graphics are a little bit different. They require that all the information is stored in the file, so the circle would be described by needs to be described in full. And pixel graphics are done in a way that the image is divided into really small squares, so they call pixels, and each pixel has a different specific color. And if the pixels are just small enough, you get a really nice image. So think about when you take a picture with your camera, so that's also a pixel graphic. But the problem is if you want to zoom in or scale it up, it may not look as nice anymore. So one has like the scaling, one gets some quality loss. The difference between the vector and the pixel graphic is also well displayed here on the right. So the text on the bottle is really small, and if we want to read it, we want to zoom in there. And if it's a vector graphic, we can really nicely read the text because it's just scaled up and we don't lose any quality. Whereas on the bottom, it's a pixel graphic and it becomes really blurry because the pixels are too big. And many of our data are plotted as lines or areas, for example, having time courses or bar graphs. So vector graphics are really powerful here. You may also have fMRI images, and they are pixel graphics, but they can be integrated into a figure that you create in a vector graphics program. There are at least 2 good vector graphic programs that you could consider using. On the one hand, there's Inkscape. That is a free tool. It has all the features available that you would need to make good scientific figures. There's also Adobe Illustrator. This program costs money, but it's a little bit more powerful, and it also tends to feel more intuitive in terms of the usability. But both programs are very suitable for making nice-looking scientific figures. It is important to emphasize that using a vector graphics program such as Inkscape or Illustrator requires having data plots already. You would need to generate data plots using your analysis tools such as MATLAB, Python, Excel, R, or any other. And Inkscape or Illustrator are then really useful for manipulating, integrating, and enhancing the data plots you obtained from your analysis tool, and then, for example, build multi-panel figures. For example, you may have some time courses obtained from MATLAB, so this is just event-related potentials from EEG, and you may have some other plots of 2 variables, and these are just a few ways you could plot them, as, for example, as bar graphs or as box plots with individual data points, histograms, another form of histograms, and just individual data points. And these data plots you would save as files and subsequently load into your vector graphics program. And the data plots in your vector graphics program would then be rearranged, enhanced, so that you can build the figure you would like to later appear in your manuscript. As I've mentioned before, vector graphic programs are really powerful for manipulating lines, surfaces, dots, and areas. So for example, some line plots or box plots or bar graphs or plots with error bars in them. So all the type of data representations we often use. But Inkscape and Illustrator can also integrate pixel graphics. They can just not manipulate them very well, at least not for our purposes. So when you get your fMRI plots from your fMRI viewer, you could use GIMP or Photoshop, for example, to remove the black background and then integrate that image into your figure that you build with the vector graphics program. And I provide on my webpage a hands-on tutorial that teach you how to get started on creating scientific figures using Inkscape or Illustrator. The final point I would like to mention relates to the figure size. So you would want to choose the correct size of the figure upfront. So when you start in your vector graphics program, so before you even get fully into it, because if you do not do that, you will likely need to rescale your figure later, or the journal will rescale the figure for you. And this will change your font size and can make your figure really unreadable. I would recommend choosing either a 1-column or 2-column figure, and then build your figure for this, exactly for this size. So you want to choose that up front. And I recommend using a 2-column figure over using a long 1-column figure, because if you have a long 1-column figure, the reader who reads on a computer may need to scroll to see all parts of the figure, and you may want to avoid that. Typically, I orient myself at the Journal of Neuroscience Standards. They provide this width for 1-column figures and for 2-column figures. They also allow 1.5-column figures, although I usually avoid this because other journals may not support this, and that it would mean that your figure may end up with a lot of white space on the left and right in the print. So to summarize, I would like to emphasize a few points again. Aesthetics really matter for scientific figures. They can really improve the impact your work has on other scientists. It can help you give more engaging talks, and it can also help you to think more deeply about your data when you think about how to visualize the most important aspects about your data. I would also like to emphasize that it's important to spend the appropriate amount of time, and that often means spending more time than you may have been used to. It is not uncommon that a multi-panel figure takes several hours to create, even with Illustrator Experience, and that is after you have plotted your data in MATLAB. I even start thinking about what the figure will look like when I plot my data in MATLAB, because that makes things easier in Illustrator later. So you may think about figure building as being as important as writing a good section in your manuscript. And building a nice figure in a vector graphics program usually comes after you plotted your data in MATLAB, in Excel, or in Python. Please choose the right figure size up front. That saves you a lot of headaches later, so that you don't need to rescale your figure at a later point. So finally, create figures that are informative, but also create figures that are beautiful at the same time. Thank you for being interested in that presentation. You can download the PDF version of it following the link here I provide at the bottom. And there's also some additional slides at the end that I haven't shown that provide additional resources that may help you with building interesting figures.